Good afternoon to one and all. I am R.V. Kiran, Assistant Professor, Department of Mechanical Engineering. Today, in this video lecture, I am going to explain you about the acceleration point of a link and acceleration diagram. So, first of all, we need to know about the acceleration diagram and the acceleration point of a link. So, in the last class, we have discussed about the motion of a link. That is, we have taken a point of motion of a link and we have substituted the values. How do we define a motion of a link? And that is the factors affecting on motion of a link. And today's topic is about the acceleration diagram and acceleration point of a link. And this is my 21st lecture regarding to the subject kinematics of machinery. So before going to a acceleration diagram and acceleration point of a link, we need to know about a small topic that is known as rubbing velocity, a pin joint. So the links in a mechanism are mostly generally connected to a pin joints, that is by means of a pin joints only. So here we are taking the pin joint sections, and the rubbing velocity is defined as the algebraic sum between angular velocities of two links which are connected by the pin joints. So these are connected by the pin joints and multiplied by the radius of the pin. So these are generally connected by the pin joints and multiplied by the radius of the pin. So that is the common definition for the rubbing velocity. So it is defined as the sum between the angular velocities of two links. So here AO link has one angular velocity and BO link has another angular velocity, which has two different angular velocities of the link, and they are connected to the pin joint O. That is, the O is the pin joint multiplied by the radius of the pin. So this pin joint has some radius integrated to it. So we are multiplying with the radius of pin. So that is the definition of the rubbing velocity. So here I am considering AO and BO, that is OA and OB, as two links which is connected by a pin joint O. So these AO and OB are two links which is connected by this pin joint O. You can see in the figure. And omega 1 is the angular velocity of the link OA, or it can be also represented as angular velocity of the point A with respect to O. But we are taking it as angular velocity of the link OA, and omega 2 is the angular velocity of the link OB. So omega 2 is the angular velocity of the link OB, and it can also be taken as angular velocity of the point B with respect to point A, because point O is the fixed end, that is the pin joint end, that is called as the center between the 2 points, the center between the points A and point B, and small r is the radius of the pin O. So small r is the pin radius of the pin, and according to the definition, so according to the definition of the rubbing velocity at the pin joint O, if the two links, that is the OA and OB, move in the same direction, that is in the clockwise or anti-clockwise. So if they move both in the same direction, we are taking the value as omega 1 minus omega 2 into r. So we are taking the value as omega 1 minus omega 2 into r. But if the links move in the opposite direction, so like this, so OA link is moving in the clockwise direction and OB link is moving in the anti-clockwise direction. So if they move in the two separate directions, if they move in two separate directions, positive form of angular velocity have been taken, that is omega 1 plus omega 2 into r. So that is the velocity to be taken, that is the angular velocity to be taken. So if they travel in the same direction, omega 1 minus omega 2 into r, that is the negative value is to be taken. But if they travel in the opposite direction, so one in the clockwise direction and other in the anti-clockwise direction, we have to take the positive value for the angular for the sum of the angular velocity. So that is the rubbing velocity for both the directions. And when the pin connects one sliding member and other is a turning member, so generally we are going to do the or connect the sliding members or turning members to these links. So if we are going to connect one sliding member and the other one is the turning member, the angular velocity of the sliding member is 0. So we are taking the angular velocity of the sliding member as 0. In such cases, rubbing velocity at the pin joint. So rubbing velocity at the pin joint is taken as omega into r. So that is the represented value for the rubbing velocity at the pin joint. That is the pin joint O, that is called as omega into r, where omega is the angular velocity of the turning member and r is the radius of the pin. So generally sliding member is going to take as 0. So that is why we are taking directly omega into r, that is the turning member angular velocity and radius of the pin. So we are taking this sliding member as 0. So that is of the rubbing velocity at the pin joint. So by taking two links, so by taking two different links with a pinned joint. Next one is the acceleration diagram for a link. So we are considering the acceleration diagram for a link. So here I am taking the 2 points. So consider 2 points A and B on a rigid link. So a rigid link means that is the fixed link. So there is no movement on that link. So we are taking the two links on that. So 2 points, consider 2 points A and B on a rigid link as shown in the figure. So this is the link taken. So AB is the link taken. Let the point B moves with respect to A. So here A is the fixed point and B is the movable point. So moving point B with an angular velocity omega. So omega is the angular velocity for the link AB and alpha be the angular acceleration of the link AB. So here alpha is also taken as the angular acceleration of the link AB. So for a link AB, sorry, for removable link AB, A is the fixed link, that is A is the fixed point and B is the movable point for the link AB, having an omega as angular velocity and alpha b as the angular acceleration. And then acceleration of the particle whose velocity changes both in magnitude direction at any instant has the following two components. So generally the acceleration of a particle changes both in the magnitude and direction. So when they both change in the magnitude and direction, they can call at any instant and has two components. So generally, first component is the centripetal or radial component, and second one is the tangential component. So by taking the centripetal or radial component, which is perpendicular to the velocity of the particle at any given instant. So these centripetal component or radial component is always perpendicular to the velocity of the particle at any given instant of velocity. But coming to the tangential component, this is always parallel to the velocity of the particle at any given instant. So that is the two basic differences between the two components, that is the centripetal component and the tangential component. So this centripetal component is always perpendicular to the velocity of the particle, but this tangential component is parallel to the velocity of the component. So by taking the link AB, thus for a link AB, the velocity of a point B with respect to A, that is we are taking it as VBA. So that is velocity of the point B with respect to A. VBA is perpendicular to the link AB. So it is perpendicular to the link AB, and since the point B moves with respect to A, so the point B is moving with respect to and with support to A with respect to A with an angular velocity of omega and with an angular acceleration of alpha. Therefore, the centripetal or radial component of the acceleration of B with respect to A is taken as, so this is moving in the perpendicular direction. So VBA is perpendicular to AB. So that is the centripetal or radial component here. So this is moving perpendicular to the link AB. So we are taking it as VBA. So therefore, radial component is equal to omega square into length of the link AB. So directly we are taking the length of the link AB. That is omega square into AB. So omega square means VBA by AB, that is V square BA by AB. So we are taking the final radial component as V square BA by AB. Therefore, this radial component of acceleration acts perpendicular to the velocity VBA. So they are going to act in perpendicular direction, that is VBA. In other words, it acts as parallel to the link AB. So whenever there is no radial component and there is tangential component, so these tangential components acts parallel to the link AB. So considerably they are going to act parallel to the link AB. Then we are taking the tangential component. So we have already taken the radial component or centripetal component. Now I am taking the tangential component of the acceleration of the link B with respect to the A. So these tangential component of the BA, that is A of BA, is taken as alpha as the angular acceleration into length of the link AB, that is alpha into AB. So we are taking the consideration as alpha into AB for the tangential component of acceleration of P with respect to A, that is the tangential component of A acceleration to the BA component, that is B point with respect to A. So this tangential component of acceleration acts parallel to the velocity. So they are going to act parallelly. So we have already known that. So the centripetal component or radial component is acting perpendicular direction to the link, but this tangential component of acceleration is acts parallel to the velocity VB. So that is parallel to this link AB. In other words, it acts perpendicular to the length AB. So it acts perpendicular to the length AB. So they are going to act parallel to this VBA position and perpendicular to AB. In order to draw the acceleration diagram for a link AB from any point B dash. So we are taking the point A dash B dash in the second diagram. Draw vector B dash x parallel to BA. So we are drawing this vector B dash x. So this is the line B dash x. So this is the line B dash x, which is parallel to the line AB. So the line parallel to the AB is taken as B dash x, and from point x draw vector x a dash perpendicular to BA. So this a dash x is drawn as parallel to this line or perpendicular to AB line. So we can take in both ways. So we can take in any one of the way, that is parallel to the line AB or perpendicular to the line AB. So I have drawn this. So this represents the tangential component of the acceleration of B with respect to A. Then by drawing these two lines, I am joining the B dash A dash. So I am joining the B dash A dash line. So this is the B dash A dash line, and I am joining the B dash A dash. Therefore, the vector B dash A dash, which is known as the acceleration image. So they both are known to be acceleration image of the link AB, which is known as vector B dash A dash, represents the total acceleration of B with respect to A, that is ABA. So it is taken as ABA. So that is the acceleration of B, that is total acceleration of B with respect to A. And it is the vector sum of the radial component. So that is the A of RBA, that is vector sum of acceleration of radial component BA, and the tangential component of the acceleration, that is AT dA. So it is known as the ABA or AT dA. So this is the acceleration diagram. So this diagram is drawn with the help of this link diagram. So by taking the link diagram, we are drawing this acceleration diagram with respect to the tangential component of acceleration. Next one is the acceleration of a point on a link. So acceleration of a point on a link. So here I am considering 2 points A and B on a rigid link. So we are taking it as again rigid link. So AB is the rigid link with the 2 points AB, and let the acceleration of the point, that is capital A, has the AA as the is known in, so acceleration of the point A, that is A capital A. Therefore, that is AA is known in magnitude and direction in the direction of path B. So I'm taking this line. So AB as the rigid link, which has 2 points A and B, which has 2 points A and B. So which has 2 points A and B, which is, and we are taking small a into a suffix capital A. So that is acceleration of the link or point A. So acceleration of the point or joint A as the, which is in both magnitude and direction, and the direction of the path of B is given. So direction of the path is perpendicular to the link AB. So which is always perpendicular to the link AB. And next, the acceleration of the point B is determined in both magnitude and direction by drawing the acceleration diagram as shown below or as discussed below. So I am taking the acceleration diagram here. So the acceleration diagram of a point B is determined in both magnitude and direction by drawing the acceleration diagram from the below link. So from the below link, I am taking the acceleration diagram. So first of all, we need to take any point. So I am taking the point O dash as the starting point. So from any point O dash, draw a vector O dash A dash parallel to the direction of A and acceleration of A. So which is parallel to this line. So draw a line O dash, A dash. So this is the line to be drawn by the endpoints O dash and A dash, which is parallel to the direction of the absolute acceleration point, that is AA, to some suitable scale. So to your convenient scale, we are going to draw this line. So we have drawn the O dash A dash line, which is parallel to the line A dash. So A, acceleration of A. So you have taken this line O dash A dash, and next we know that the acceleration of B with respect to A, that is ABA, has the following two components. So generally we have discussed in the earlier point also. They had 2 points, two components. First one is the radial component and second one is the tangential component. So they has two components, radial component and the tangential component. So first one, this radial component of the acceleration of B with respect to A. So that is R suffix ABA. So R is the radial component of acceleration of B with respect to A. So here small a is the acceleration and R is the radial component. BA is the acceleration of B with respect to A. So this is the term we used for radial component of acceleration of B with respect to A. And in second one we had tangential component of acceleration B with respect to A, that is TA of BA. So TA of BA, that is tangential component of the acceleration B with respect to A. So these components are mutually perpendicular. So they are going to perpendicular direction, and I am drawing the another line. So draw vector A dash x parallel to the link AB. So I am drawing the A dash x line. This line is perpendicular to the parallel to the link AB. So this is the link. So which is parallel to the link AB. So this is the link and this is the actual link to be drawn. So they are both parallel to each other. Because radial component of the acceleration of B with respect to A will pass through AB. So they are going to pass through AB such that vector A dash x is equal to. So we are going to find these components A dash x, that is vector A dash x is equal to radial component of acceleration B with respect to A that is equal to velocity of the square of B with respect to A by AB. So this is the value to be taken. So that is vector A dash of x. So that is vector A dash of x is taken as radial component of the acceleration B with respect to A, and they are going to be v square ba, that is velocity of the b with respect to a square divided by ab. So this is the component to be taken as vector a dash x for the components a dash x. So I am taking it by step. So you need to know and understand how to draw the acceleration diagram. So point wise గా ఎక్స్ప్లెయిన్ చేస్తున్నానమ్మా, మీరు ఈజీగా డిఫైన్ చేసుకోవాలి. సో పాయింట్స్ అనేవి ఎలా తీసుకుంటున్నానని. నెక్స్ట్ డిఓఎం లో వస్తుంది మనకి యాక్సలరేషన్ డయాగ్రామ్, దాంట్లో డ్రా చేయాలి. సో అక్కడ నేమ్ చేంజ్ అవుతుంది. సో నెక్స్ట్ ఐఎమ్ గోయింగ్ టు ది లాస్ట్ స్టెప్. So we have taken the 2 points. So that is O dash, A dash and A dash X. So from the point X, I am drawing the vector X B dash. So that is the X B dash. That is the in the dotted line. You can see that X B dash. So I am drawing the vector X B dash, which is perpendicular to the line AB. That is, I am taking the tangential path of B. That is tangential of acceleration B with respect to A, which is perpendicular to the link AB. So here also I am taking that because tangential component of B with respect to A, that is tangential component of A, sorry, B with respect to A, which is perpendicular to radial component, that is ARBA. So that is perpendicular to the direction ARBA, and through O dash draw a line parallel to the path of B. So draw a line parallel to the path B, that is AB. Therefore, the vectors xb dash and O dash B dash intersect at B dash. So here I am drawing this O dash B dash line, which is parallel to acceleration of B. This is the acceleration of B line. This line is parallel to O dash B dash. So this is the acceleration of the line B. So this line is parallel to O dash B dash. And from these 2 points, that is x b dash and o dash b dash, there is an intersection of point. So this is the intersection of point for the two lines, that is o dash b dash and x b dash. Now the values of acceleration of b and tangential acceleration of b with respect to a may be measured. So అలా మనం ఈ టూ వాల్యూస్ ను కూడా మెషర్ చేయొచ్చు. సో ఈ డాటెడ్ లైన్స్ లో x నుంచి b డాష్ తీసుకున్నాం కదా పాయింట్, నెక్స్ట్ o డాష్ b డాష్ ని కూడా జనరేట్ చేసుకోవచ్చు. సో రెండింటి యొక్క మెజర్ అనేది మనం క్యాలిక్యులేట్ చేసుకోవచ్చు. నౌ ది వాల్యూస్ ఆఫ్ AB and tangential acceleration of BA may be measured to the scale. Then by joining the points A dash B dash, we may determine the total acceleration of B with respect to A, that is ABA. సో ఇంకా లాస్ట్ మనకి ఇది ఒక్క లైనే కదండి ఉంది. సో A dash B dash అనేది కూడా మనం జాయిన్ చేసేస్తే సో మనకి యాక్సలరేషన్ ఆఫ్ B with respect to A అనే పాయింట్ అనేది వచ్చేస్తుంది. సో యాక్సలరేషన్ ఆఫ్ B with respect to A, that is ABA is to be formed. So the vector A dash B dash is known as acceleration image of the link AB. So I am taking as the vector A dash B dash is known as acceleration image of the link AB. So that is A dash and B dash. So they are going to the acceleration image of the link AB, and the angular acceleration of the link AB is obtained by dividing the tangential components of the acceleration of B with respect to A, that is by dividing the tangential components of acceleration. So that is ATBA to the length of the link. So the angular acceleration is taken as ABA by total of the link. So the angular acceleration of the link AB is obtained by the dividing the tangential components, that is tangential component of acceleration of B with respect to A to the length of the link. Length of the link means AB. So AB is the length of the link to be taken. Therefore, mathematically, angular acceleration of the link AB is taken as, that is alpha of AB is taken as tangential acceleration of the link B with respect to A divided by link of AB, that is the link AB. So it is taken as alpha of AB is equal to tangential acceleration of the B with respect to A divided by length of the link AB. So length of the link AB to be taken. So therefore alpha of AB is calculated, that is angular acceleration of the link has been calculated. So this is the process by taking the or for measuring the angular acceleration by the acceleration diagrams. So this is the process to be done. So for every acceleration diagram for a point of a link, we need to draw these acceleration diagrams consistently. So by this, I am ending this class. Thank you.